Understanding activation functions in neural networks step by step. Imagine a neuron in a neural network. It receives information from other neurons through weighted connections, like tiny messages telling it how important each piece of information is. But just receiving this information isn't enough. The neuron needs to decide how important this combined information is and whether it should fire its own signal to other neurons. This is where activation functions come in. They act like gatekeepers, taking the weighted sum of all the inputs the neuron receives and transforming it into an output value that determines whether the neuron gets activated or not. Here's a step-by-step breakdown. Step 1. Receiving inputs and weights. The neuron receives input values from other neurons. These values can be anything from raw data points to outputs from previous layers in the network. Each input is associated with a weight, which tells the neuron how important that particular input is. Step 2. Calculating the weighted sum. The neuron multiplies each input value by its corresponding weight. It then adds all these weighted values together to get a single sum. This sum represents the combined strength of all the incoming signals. Step 3. Applying the activation function. This is where the magic happens. The neuron applies the chosen activation function to the weighted sum. The activation function is a mathematical formula that transforms the sum into an output value between a specific range, usually 0 and 1, but it can vary depending on the function. Step 4. Interpreting the output. The output value from the activation function tells us how activated the neuron is. A high output value, closer to the upper limit of the range, means the neuron is strongly activated and will likely send a signal to other neurons. A low output value, closer to the lower limit, means the neuron is weakly activated or not activated at all, and its signal won't have much impact. Why are activation functions important? They introduce non-linearity into the network. Without them, neural networks would only be able to learn linear relationships, which limits their ability to handle complex tasks. They prevent vanishing or exploding gradients during backpropagation, a crucial process for training neural networks. They add expressiveness to the model, allowing it to learn more intricate relationships between the inputs and outputs. Examples of activation functions. Sigmoid outputs a value between 0 and 1, like a probability. Commonly used in early neural networks. ReLU, rectified linear unit, outputs the input directly if it's positive, otherwise outputs 0. Simple and efficient, popular in modern deep learning. Than, similar to sigmoid but outputs values between -1 and 1. By understanding these steps and the role of activation functions, you can gain a deeper appreciation for how neural networks work and learn. I hope this explanation helps. Feel free to ask if you have any further questions.